Till now in the series, we learned the basics of transformers along with their working concepts and creating them from scratch for different use cases like text classification, language translation, and text summarization. But for every use case, we trained a different model with a little modification in model's architecture. But what if I tell you that if a single model can alone perform all these tasks without modifying its architecture or retraining, and that's not a large language model, and that model is called text-to-text transfer transformer or T5 for short. So let's talk about how this is different from traditional transformer we built till now. 1. T5 uses text-to-text approach, which means it converts all NLP tasks into text-to-text format. It takes an input and generates text as output. For example, to classify a sentence, it would translate the sentence into a label like positive or negative. T5 uses a unified pre-training or fine-tuning method, which means it learns from a large amount of unlabeled text using single objective, predicting masked words. Let's understand this by an example. Suppose you have this sentence, and we train a model to predict this masked token. The model computes probabilities for each possible words that could fill in the blanks. In this case, it might predict lazy based on context. This helps it acquire general language knowledge that can be transferred to different tasks. T5 uses task-specific prefix to guide the model during fine-tuning, which means it adds a specific token at the beginning of the input text to indicate what task is it performing. For example, to translate from English to French, it would add a token, translate English to French, before the input sentence, or use prefix summarize and use sentence. This uses model's language understanding to perform different tasks without training a dedicated model for it, which makes it highly scalable. You just need some data and you can easily fine-tune to make it learn a new task, which is what we are going to do in this video. This model is large, so I would recommend you to use Google Colab for the coding part if you don't have a GPU VRAM of 10 GBs or higher. So let's begin. I'm using CoQA, which stands for Conversational Question Answer Dataset. In the dataset, you will find context and question from that context. It's like comprehension. And this time, I'm not going to train it from scratch because that will take immense amount of compute resource, which I don't have. So we'll fine-tune using Huggingface transformers, and for the very first time on the channel, we'll use PyTorch. Link to the dataset is in the description. Download it and let's start with the coding part. Import libraries like PyTorch for machine learning and for making dataset pipeline, transformers for getting pre-trained model, and tokenizer. Load the dataset into memory using pandas, and here the dataset is actually JSON. So we need three things from this data: story, which will act as context, question formed from the story, and answer to those questions. So for now, we have a list of questions and their answers, and we need to convert this dataset into tabular form so that every row has a context, a question, and an answer to that question. So let's do that first. Define column names for context, questions, and answers, and for every sample, run the loop for how many questions are there. And then store the same context for every question and the answer in a temporary list. And at last, use a final list to insert into data frame. And see, we have just created a dataset for training. Now load the pre-trained tokenizer for T5 model and T5 model itself. Load the optimizer and go with a slower learning rate. Define some parameters like query length, which is question, and target length, which will be the answer to the question. Batch size according to your GPU, device to train on, and as we are using PyTorch, we need to transfer the model to GPU memory. Now model is loaded, it's time to make the data pre-processing pipeline. Define some variables for getting tokenizer, source and target length, data, question, context, and answers. For the pipeline, get the question context and answer and feed the context with question in tokenizer to get the tokens, and then pass the answer to tokenizer to get the answers token. Now usually, Huggingface tokenizers return multiple things along with the tokens in a dictionary, like input IDs, which contains actual tokens, attention mask, which is a list of indices specifying which tokens should be attended by the model, and so on. We need these things only to fine-tune our model. Get the tokens for answer and convert it into PyTorch tensor. and replace all zeros in the token with minus hundreds, which is a message for loss function in PyTorch to ignore these values while computing loss. Now return token for questions, attention marks for question, answer tokens, and attention marks for answer tokens. These are the final values which will be fed to model. Split the dataset for training and validation, and shuffle the sample for both sets using random sampler. Define the data pre-processing class and use the PyTorch data loader to create the dataset pipeline for training and validating the model. Now with proceeding towards training, define some variables to store training loss, validation loss, number of training and validation batches fed into the model. For each epoch, model.train which will tell the model that it is in training mode, and for each batch, load tokens, attention mask, answer tokens which is labels here, and answers attention mask into GP memory. Now feed these inputs into model to get the prediction. Reset optimizer and calculate loss for backpropagation. Apply gradient descent, capture the loss and increase the batch count to +1. Now use the model event to tell the model that it's now in evaluation mode for the validation part, and do the rest of the thing as same as we did for the training. At last, print the training and validation loss per epoch and hit enter to start model training. The dataset is large and batch size is low, so it will take a lot of time for me. It took almost 2 to 3 hours per epoch, and I'm using RTS 3060 which has around 3500 CUDA cores. Google Colab has slightly more powerful GPU. If you use that, you may have to spend less time training the model. And once you finish with the training, save both model and tokenizer locally. Now let's create a function to run the inference. Use questions and context together with tokenizer to get the tokens for them. Convert the tokens and attention mask to tensor, and then feed those inputs to model to get the predicted output. Now again, use tokenizer to decode the predicted output, and don't forget to use skip special token to avoid getting tokens like CLS or SEP in output text. And now you have answer to your question according to the context. You can also compute BLEU score, which stands for Bilingual Evaluation Under Study Score, which is a metric to evaluate a generated sentence to a reference sentence. So if you are passing reference answer, then load the metric and use the compute function to get the BLEU score as a match result. Now print context, question, reference answer, and predicted answer and BLEU score. Now get a sample from the data we have and pass it to predicted answer function and hit enter. And here it is, context, your question and predicted and original answer with the score. And happy to see that it predicted correct, although the answer is short but is correct. And this was the way to use transformer by fine-tuning it in the easiest possible way, where you have all the controls over pre-processing and output. I hope it helped and will continue to retrain, fine-tune, creating new model and some creative projects as well as for this series. Please drop down your ideas which you wanted to see in upcoming videos and in the comments, and as always, thanks for watching.